Okay, keep in mind, collecting training data, as I mentioned earlier, that it is not necessarily a difficult job nowadays, but it still takes a lot of time to label your data. Okay, collecting data may not take a lot of effort. You can just write a crawler, web crawler to collect the data, but to label data a lot of time require like a special expertise. Okay, for example, okay, let me, okay, sometimes if you want to train a model that determine a cat picture, not necessarily cat, okay, a picture is cute or not, okay, object, okay, it could be a person, it could be a cat, it could be a dog, okay, this object is cute or not. Can you write a, then you need to collect a lot of pictures, of objects, and then, with label, oh, this is cute, this is not cute, right? But who to label this? It takes a lot of manual work to label this data, right? Because obviously you cannot let the machine to do the labeling. I mean, if the machine can do this labeling, you already have a model to do the job, right? Okay, so this is like a, catch-22 a lot of time. You need a lot of like effort to label the picture. Okay, even though data collection may be easy, but it may be too costly to label. Okay, the third one, with such a large network, training would be extremely slow. Okay, when the training could take a long period of time, is there some way to speed up training? Okay, after all, like we are not, even the computer hardware improve like year after year, it's still quite annoying. Okay, if each training take like days, right? Yeah. So how do what can we do to speed up the training? And last one, a model with millions of parameters would severely risk overfitting. So as I said, we need to know more techniques to fight with overfitting. We already talked a little bit about that, but this chapter, in the chapter 11, we are going to go over these problems and talk about the solutions, or at least like techniques to alleviate this problem. I cannot say like those solutions can completely solve the problem. That's just probably is just not possible. But at least like it will make the problem, alleviate the problem. To make it like much better. Okay. So the first one is vanishing exploding gradient. Okay, so what is vanishing exploding gradient? Okay, so remember like in previous chapter we already talked about how to train the model, right? The model training in deep learning, rely on back propagation, right? Back propagation, and back propagation rely on computing the gradient, right? Computing the gradient. Gradient, what is the gradient? Gradient is slope, right? Basically it's slope. But a lot of time, okay, you will find that, okay, the gradient, okay, that pass, layer by back to layer by layer, okay. From, remember, it's a reverse, back propagation. From the term, remember we talked about, okay, we first like compute like the difference between the, we first feed the training data into the model, and then we obtain the result from the output, right? And then we check like this output. I mean, we calculate the difference between the output and the ground truth to determine the gradient, right? And then we will compute this, one layer at a time, backward, okay, to the first layer, right? So layer by layer, back propagate to the first layer, right? But this back propagation, okay, sometimes you will find that, okay, the gradient for each layer becomes smaller and smaller and eventually vanishing. When I say vanish, I mean like it's very close to zero. But when the gradient, when the slope is close to zero, that means what? That means your training will not go anywhere, right? Because the training, okay, the direction of the training rely on the gradient, right? Okay, but if you don't have a gradient, you don't have a place to go. So your training will stall. You will stop there indefinitely. Okay? So that's the first issue. Okay. The other possibility is exploding gradient. It's exactly the opposite. Okay. Remember, like in the model training, not only we need a gradient, but also the size of the gradient vector determine how far we go for each step, for each iteration, right? Of course, it's determined not only by that, but also by the learning rate, right? But at least you guys know like the size of the gradient vector has an impact to how far you go for each step, each training step, right? So sometimes, okay, the gradient could become bigger and bigger. So eventually it becomes too big. So the training will do like kind of like a jump around. In the space, in the training space, it will just go like at different places, and it doesn't converge because the gradient becomes too big. We call that exploding gradient problem. Okay, to be honest, okay, vanishing gradient happen more often than exploding one. Okay, the exploding gradient normally happens only in certain neural networks, such as RNN. Okay, which has because RNN has a feedback mechanism which make the gradient to be more likely to explode. Okay, but for most of the other neural networks, the problem mostly is the vanishing gradient. Okay, so what do we do? What do we do? So this is actually, remember I told you guys like the neural network, or I should say like a second wave of the AI died around like end of 1980s at the beginning of 1990s, right? And it doesn't, the third wave of AI, which is now, okay, it's like come back around like around year 2000, right? I mean, as I say, like there are some reasons. One of the reasons is because some small tweaks, right? So those small tweaks has something to do with this. Okay. So first, let me explain the reason for this. Okay. The vanishing gradient. Remember, like I talked about this before. Like the ANN originally got the idea from BNN, right? Biological neural network. Okay, and the activation function in the biological neural network, okay, is kind of like a sigmoid. Okay, sigmoid. So you know sigmoid, the shape of sigmoid, right? It's S shape, right? S shape, right? So on two sides of this function, the gradient, the slope is almost zero, right? Okay, we call such a phenomenon as saturating. Saturating. When a function is saturating, okay, its gradient is close to 0, such as here and here. Okay, so because in the second wave of AI, people still believe in God. No, I'm saying like we are still believing in God. Okay, yeah, no religious incorrectness here. Okay, I mean, because people still think like the AN should follow BN closely. So most of them use sigmoid, okay, as activation function. And the sigmoid function, you can see that when it gets a larger value or smaller value, okay, you are going to get like a close to 0 gradient, right? So this is like one of the reasons that contribute to the vanishing gradient. Okay, so another thing that have been observed. Okay, this is like one of the small tricks that actually has important consequence to the third wave of the AI, is that, okay, these two guys, Glorot, Benjo, especially Benjo. Glorot is actually Benjo's student, okay? But Benjo is a nice professor, so he let his student to be the first author, because like this paper has a very important impact. So this technique is named after his student's name. To be honest, like this technique should be named after Professor Benjo, but it's named after because his student is Glorot Xavier. So this is called Xavier initialization. So what they found is like this. Okay, in the back propagation, okay, if at that time, back in the old days, okay, people use like Gaussian distribution with average 0, standard deviation 1. Okay, so basically just like the standard Gaussian to randomly initialize the parameters in the model. Okay, so this is like followed, by pretty much everyone. Okay, back to the second wave of AI. But they found that, this is important, they found that if you use this initialization, then when you do the back propagation, the variance will increase layer by layer. So when the layer increase layer by layer, what does that mean? The value will become more and more fluctuated, right? So when the value become more and more fluctuated, it goes to these two ends, right? So when it goes to these two ends, you are getting no gradient. Okay? So that is the cause of the gradient, vanishing gradient. Okay? Of course, this has to do with two things. First, the activation function. The second one is the initialization technique at that time. Okay, so they did some research and then derived that, okay, there are other better initialization technique. And of course, after that, people start not to use sigmoid as activation function that much. People use, for example, nowadays ReRU, right? ReRU doesn't have that issue, okay, anymore. Okay, so, well, I think we don't have time to talk about the Xavier initialization today. So let's stop here today. We'll talk about Xavier initialization next time, okay? Okay, so I'll see you next week, okay?